Patients, welcome again. It is customary to finish with a bang, and appropriately the title is, well, appropriately we introduce Michael Thaddeus from Columbia, and his title is the Universal Implosion and the Multiplicative Horn Problem.
Thank you very much. Thank you, and thank you to, welcome to the viewers watching at home. If I'd known this was going to be filmed, I would have got a haircut.
You look beautiful.
Is the mic on?
What?
Oh, so this. Hello?
No. All right, good. And thank you for the invitation. I volunteered to speak last because my lecture is going to be quite different from the previous ones, and it's sort of in the vein of light relief. I have no results, and it also will contain no algebraic geometry. That's true. You'll see what I mean. There is algebraic geometry lurking in the background underneath the whole the topic, but really I'm going to talk about linear algebra in some sense. And specifically about the Horn problem, the multiplicative version of the Horn problem, which is about eigenvalues of products of unitary matrices. But the clicker isn't working, so I have to go over here. All right. So let K be a compact lever, but I've tried to highlight the important actors in the drama in red. So far so good. Let delta denote the set of all conjugacy classes in this group. What the multiplicative? Well, no, thank you. I think it's better. I have a lot of clicks. What the multiplicative Horn problem asks is, what constraints do the eigenvalues of two unitary matrices place on the eigenvalues of their product? So how do the conjugacy classes of AB constrain the conjugacy class of AB? And I can think of it as saying, well, consider the set of triples. If I let C be the inverse of AB, consider the set of triples, ABC, where A times B times C equals I. But where's the laser pointer?
The red button.
The red button. Yes. All right.
Slowly.
Yeah. What is the image of this natural map? So it's a map from a compact set, right? So you know it's going to have compact image. And it's clear that this image is not all of delta Q because, A is the identity, then B and C must lie on the diagonal. There are many generalizations of this question, and I'm not going to discuss them. One could, for example, consider products of more than two elements, or one can consider some general situation involving a homomorphism from one Lie group to another. But for simplicity, let's just consider this simple case. Well, what is the space of conjugacy classes, first of all? It quickly reduces, or one can quickly reduce the problem to the case where K is a simple group. And in this case, the set of conjugacy classes can be identified with a simplex. If you get bored, you could think about the case of U2, the unitary group. In that case, the space of conjugacy classes is a Möbius strip. So we don't want that. Let's assume that the group is simple, like SUN. The reason it's a simplex is because, well, consider all the usual machinery, a maximal torus, the Lie algebra, and so on. The W is the vital group. Then any element of a compact Lie group can be conjugated into the maximal torus. That's well known. So K mod K is T mod W. But then T mod W, of course, further I can regard T as a quotient of its own Lie algebra by the exponential map. And so it's really a quotient of this vector space T by W tilde, the affine vital group, which is the semi-direct product of the co-character lattice and the vital group, acting by reflections in affine hyperplanes. And a fundamental domain is the so-called vital alcove, and that's a simplex. Here is a picture in the case of SU3, right? That's the algebra of the maximal torus is two-dimensional, the Bob group reflects in those lines, and a fundamental domain for the action is that blue triangle. Just in the case of SUN, it might be good to spell out exactly what's going on. What the simplex is really parametrizing is the logarithms of the eigenvalues. I take the logarithms of the eigenvalues of a unitary matrix. I divide by 2 pi I, so the real numbers. I arrange them in decreasing order, and I can always arrange that they lie in an interval of unit length, and that the sum of the logarithms is 0. I can arrange that if k is in SUN. And so that's my simplex. You might ask, what are the vertices of this simplex? What kind of matrices do they correspond to? In the case of SUN, they correspond to the elements of the center, the entrance of unity. Now, I should say that the multiplicative horn problem is solved. This is not a talk about how to solve the problem, because it has been solved over the last 20 years, I guess, chiefly by the work of Belkale and Vasser, but with contributions by a number of other people, some of whom I've mentioned up there. And if I left out any names, please tell me. I'm sure I did. The important part of the solution for our purposes is simply that the image of that map that I mentioned before, the set of triples of conjugacy classes that can be taken on by 3 matrices whose product is 1. That's a convex polyhedron inside this its product of 3 simplices. It's a sub-polyhedron. That's the important part. And this polyhedron is going to be the, the main focus of the talk, the protagonist of the drama. Let me pause to see if I can get these to work. It would be so nice if, well, I do? I am trying all of them. That's right, the computer, it blinks so it knows that I'm doing this, but it's just doing it to vex me. All right. I give up. Right, let me tell you briefly the solution to the problem, although I'm never going to use it. Because this is the only time that you will see algebraic geometry in this talk, and that's true. We know that any subset of the set of numbers between 1 and n, the set of natural numbers, determines a Schubert cycle in the Gauss-Montian of R-planes in n space. And I can take the Poincare dual of that class, which is in the cohomology. And then whenever the corresponding Gromov-Witten invariant of the Gauss-Montian, the degree d Gromov-Witten invariant of the triple sigma I, sigma j, sigma k is exactly equal to 1, it's not 0 and it's not greater than 1, then that determines a facet of this polytope P. Alright, these are the alpha I, beta j, gamma k are the eigenvalues of A, B, C respectively. Alright? So that's the answer. And then, if you want to know the answer, you can go home. Let me illustrate it in, the simplest case, and this is maybe deceptively simple. The space of conjugacy classes in SU2 is parametrized by an interval. The simplex is simply an interval. So delta 3 is a cube, and the polytope P, the polyhedron P, is a regular tetrahedron. There it is. There are 4 faces, and those 4 faces, 3 of them come from degree 0 Gromov-Witten invariants. They come from Gromov-Witten invariants of the form, point, fundamental class. Those are the 3 faces that touch the origin down there. And then there's only one non-trivial Gromov-Witten invariant, which is the one, it says that there is a unique line in P1 passing through 3 points, alright, which I think we knew. But that determines that's the degree 1 invariant that determines the face that does not pass through the I should mention also that, you might say, well, that's not a complete solution of the problem because it expresses it in terms of something inexplicit, namely, quantum cohomology of Gauss-Montians. That's true, but we actually know a lot about that subject as well. We have Pieri, Gambelli formulas, and so on. We can calculate it. So using that, Belkale turned that into an explicit recursion in N. It's giving you some kind of explicit inequalities telling you what the, sort of what the facets are. Only at the present state of the art, I guess this is not perfect. He doesn't know an infallible way of finding all the facets, just some finite set of inequalities that includes the facets, but also some redundant inequalities. Nevertheless, if you want to check that some point is in the polytope, you have a way to do it. You can put it on a computer, which I did.
Did you say it involved genus 0 and their genus 0?
Oh no, and genus, all degrees, but only genus 0. I should have said, right? These are only genus 0 going with it, right? Yeah. But an interesting question whether there's any meaning to the higher genus invariance in this setting. But should ask Belkale that question. Alright. I'm not going to discuss, therefore, the question of how to solve the Horn problem in this, the multiplicative Horn problem in this sense. In this sense, the problem is basically solved. Instead, I'm going to discuss how to solve it in a different sense. And I hasten to add, I do not have a solution, but I at least open the question. The dual question, instead of asking for the facets of the polytope P, what are its vertices? That's a very natural question to ask about any polyhedron. And as far as I know, this question is completely open. I asked the experts, they said, we don't know. Can one in any sense give a complete list? Is there a recursive formula? Is there a completely explicit formula? And you know, what I would like to do would be to walk here on the stage and tell you that I know, but I don't know. I thought I knew. I thought I had some inroads into this problem, but you know, I have fewer inroads than I thought I did. Of course, all you have to do, in principle, is solve a linear programming problem, right? There is an algorithm if you know the facets of a polyhedron to find its vertices and vice versa. And again, you can put this on a computer, it works, but it gives you no general formula, no general insight. For any particular, the group, you can certainly do it. And I did this. Is this software package polymate? In a few minutes, it found the vertices for SU6. That was in October, and it is still thinking about it. So you see that the complexity of the problem grows explosively.
But how many vertices are for this?
A lot. Thousands. Yeah. I mean, the problem is you start with Belkale's list, and that is highly redundant. So I don't even know exactly how many facets there are. I'm not sure that is known. Well, yeah, I'm not sure that the number of facets is known. But in the thousands. And then, of course, these polytopes have a high degree of symmetry, but the software doesn't know about that. Okay. So instead, I want to make a geometric interpretation. Anyone that's thought about this question, of course, knows this, that one wants to think in terms of flat connections on a trinion. A trinion means a sphere with three disks removed. And its fundamental group, of course, is the free group on three generators, modulo the one relation ABC equals 1.
So you're against pants?
You know, I went to graduate school in England, and in England, pants means underpants, right? And therefore, this term was not used. Yeah. So yes, I'm against it. There are the three generators. I've drawn them in red. And I guess it's obvious at this point that therefore if you have a triple of unitary matrices or elements of a Lie group K that multiply to the identity, you get a flat K bundle on this trinity. So let's look at the modular space of these things. If you fix the conjugacy classes, and this is again well known to the experts in this business, then the modular space of such flat bundles is, I want to say, a symplectic manifold. Well, there can be, objects with automorphism, so it acquires singularities, but it's still, the symplectic people are okay with that. They call it a symplectic stratified space. It has strata that are symplectic manifolds, they glue together nicely. And as a matter of fact, it is, and there's secretly some algebraic geometry, secretly it is a complex projective variety. But I won't discuss why, because we have to catch our train. Anyway, the polyhedron that we're studying, right, is simply the set of all triples of conjugacy classes where this modular space is not empty. And when you start thinking symplectically, you want to look for the moment map of a torus action on a symplectic manifold. In symplectic geometry, the way the polyhedra arises is the images of moment maps of torus actions. There's a theorem which is due to Atiyah, Gilman, Sternberg, and again, maybe some others, extremely well known, that says that if a torus acts on a compact symplectic manifold with moment map, from M to T star, then the image of the moment map is the convex hull of the image of the fixed point set, which is a finite set. And if M is only a symplectic stratified space, not a symplectic manifold, it doesn't matter. This will still be true. So the question in our setting is, can we find a space like this, which in the old days we used to call a master space, a symplectic manifold or stratified space with a torus action, and the action in this case is going to be of 3 copies of the maximal torus of the Lie group. That, if you think about it, that's what you would expect. Can you find such a thing, such that the moduli spaces in question appear as symplectic quotients at different values of the moment map? If so, then the vertices of the polytope would appear as images of fixed points.
So here, the torus is S1, 3, or?
No, it's T3, where T is the, again, T is the maximal torus of K. I'm going to tell you what this M is in a minute. And then
It's not C star.
no, it is the maximal torus of K to the 3. Yes. Right. T is the maximal torus of K. I mean, how can I be more clear? Right. Yes, T is the maximal torus of K. Alright, so you can find this in the literature actually, although they're much more preoccupied with higher genus, so they don't think about the genus 0 case, you know. Right, and you can find 2 papers by Pertubis, Jeffries, Kumar. One where they construct it as a quasi-Hamiltonian quotient, which I'll proceed to explain. Another where they give an algebraic correspondence theorem, and they claim that this makes it a complex predictive writing. I'm not 100% convinced, Maybe it's bad to speak ill of somebody else's research when they're not there to defend themselves, but they never say exactly what the stability condition is. So I'm not totally sure that it is a complex predictive writing. But, yes.
So is the question about polyhedron equivalent to asking when master space ends empty?
No, the master space contains all of it. It's asking when the quotients are empty, right? It's asking when the quotients are empty. So we're asking about the image of the moment now. Is that all right?
So you can like vary alpha, beta, and gamma.
Exactly. And that, as alpha, beta, gamma varies, those are different points in the image of the moment. All right, so let me tell you what a group valued symplectic quotient is. This is not, unfortunately, a vanilla symplectic quotient. It's a group valued symplectic quotient, and this was a concept introduced by a remarkable paper by Alexeyev, Malkin, and Meimer. This is actually, in some sense, the only example of a group valued symplectic quotient. It's a theory that has, very few examples, but very important examples. There's a notion of a quasi-Hamiltonian group action of a Lie group G on a manifold M. That means that there is an invariant 2 form on the, G invariant 2 form on the manifold, and there is a moment map that goes not to the dual of the algebra, but to the group. And these 2 structures have to satisfy certain conditions. For example, the exterior derivative of omega, rather than being 0, is supposed to equal the pullback of the canonical 3 form on the group. And there's other conditions like that that sort of perturb or generalize the usual moment map conditions. And then they define the quasi-Hamiltonian quotient to be mu inverse of I mod G, just as it is in the usual case. Now, if G is a torus, all of these conditions just boil down to the regular ones, and the moment map is the classical moment map, modulo exponentiation. But then they also show, not surprisingly, that if there are 2 commuting group actions, you could divide out by one of them and you get a quasi-Hamiltonian action on the other one. But the interesting consequence of that is that if one of the 2 is a torus, or such as a trivial torus, 1, but even if it's a non-trivial torus, then the M mod G is symplectic, even if M itself was not symplectic. And that's the situation we're going to find ourselves in here. The animal that the non-abelian group acts on is what's called the Universal Implosion. Yeah, why? That name always makes people laugh. I did not invent that name. That name was invented by Gilman and Jeffrey and I don't know, somebody else, maybe Sternberg. It's sort of like a blow down, right? But what it's supposed to be, I'll tell you in a sketchy way what it is. It's a quotient space of K times T, of a compact Lie group times its maximal torus. We have this natural map from a group to its space of conjugacy classes, which I regard as contained in the Lie algebra of the maximal torus. A section of this map is provided just by the exponential map. And the centralizer of an image of this section depends only on what face you started in. So let KF be the semi-simple part of the centralizer of that element. And then all I do is I take homogeneous spaces of these centralizers and I multiply them by the corresponding faces. That's the universal implosion. But the point is there's a natural surjection on this thing from delta times K, right? And I give it the quotient topology, but more than that, it's, it has a natural, it becomes a stratified space where the strata are these things appearing in the disjoint union. So this is a quasi-Hamiltonian stratified space with the, what makes it quasi-Hamiltonian is the action of the natural action of K times T, where Kx on the left on this factor and Tx on the right on that factor, okay? T normalizes Kf, so it can act on the right. And I wrote down what the group valued moment map is.
Michael, for those of us that are stuck in the world of like SU2, can you...
Oh, I'm coming to that, yes. What is this thing for SU2? Yes, I'll tell you in just a minute.
Okay.
But the master space, anyway, I take the diagonal action of K on 3 copies of Q, and I divide it, and I still have the residual action of 3 copies of T. So the point is that this now is, by what I said before, is a symplectic stratified space. And, I claim that it has this master space property that, that the original space that interests us, M alpha beta gamma, is a symplectic quotient of this thing at the point alpha beta gamma. Oh, so, to answer your question, when K equals SU2, what is Q? We have, again, the simplex in this case is just an interval. I have the conjugacy class of plus the identity, conjugacy class of the minus the identity, and everything in between. All I do is I take S3 times that interval and I collapse the two ends. So that's the suspension. And the universal implosion in that case is nothing but S4. The fact that it's smooth is sort of an accident of the situation. In general, Q is singular and M is singular, but in this case it happens to be smooth. And so the symplectic quotient in this case of S4 cubed mod SU2 is CP3. It's kind of cute. But this is a fact. But S4 is not symplectic, but CP3 is. And that's what you expect. There's a toric variety whose image is under the torus action. Yeah, the smoothness is excellent. All right. So I want to interpret this as the modular space of something like that bundles. So I'm going to use, instead of a circle, I could use a circle, but it's easier to use a lollipop, a circle with a prong sticking out, just for simplicity. Put my base point there at the end of the prong. Of course, a flat bundle on the circle, if I trivialize it at one point, such things trivially are just completely determined by their holonomy around the circle, right? Which is a well-defined element of the group. But the structure group of such a bundle canonically reduces to the centralizer of the element. I can take the associated bundle, TA bundle, where I divide out by the commutator subgroup. I get an associated torus bundle. And what you can convince yourself is that Q is the moduli space parameterizing, a very silly thing, right? Flat K bundles on these things, trivialized here, but also with a global trivialization of the associated torus bundle, which is trivial, but not canonically so. So, let me illustrate again in the case of UN. In the case of UN, I think of my universal implosion Q as parameterizing flat unitary vector bundles on the circle or on a lollipop, framed at one point, but also with the trivialization of the determinant line of every eigenspace of the holonomial. And, of course, the dimensions of the eigenspaces jump as you move around. So what does it mean to have a moduli space? What does it mean for it to represent this problem? It means there's some notion of families, and that's what gives you the stratification on this stratified space. And, I said at the beginning we assume that the group is simple, so you could assume that K is SUN instead, but then, of course, the trivializations of these determinant lines have to be compatible with the overall trivialization of the determinant, which is an annoying condition, but We want our groups to be simple. Well, once we understand that this is the modular interpretation of the universal implosion, what's the modular interpretation of the master space? Well, the dividing by decay action erases the choice of the framing. If you remember, I drew the trinion with those 3 lollipops sticking out of it, right, which are all glued together at P. So I have flat bundled on the 3 lollipops. The condition that ABC equals I means that the flat bundle extends over the trinion. So it's clear now that the space I constructed is the modular space of flat K bundled on the trinion, together with trivializations of the associated TA torus bundle of the centralizer of the holonomy on each boundary circle. That is, again, in the case of the unitary group, I look at the holonomies around the boundary, I look at their eigenspaces, and I trivialize their determinant lines. So what is a fixed point? A fixed point is one where there exists global automorphism to this bundle, canceling out the action of the torus, which changes the trivializations of those determinant lines. And what's a global automorphism of a flat bundle? It's completely determined by its value at any one point, isn't it? So it's really just an element of this centralizer, common centralizer of A, B, and C. There has to be such a thing that surjects onto these 3 tori. And that, translates it purely into a statement about linear algebra or about Lie theory. One can search for these things. Now, of course, one possibility is simply that all 3 of these tori are the central parts of the centralizers of the holonomy. So one could say, well, maybe those things just have to be trivial, right? And that happens if the holonomy is central. So one possibility, of course, is that all 3 of these things are trivial, and that means that the holonomy is central. Well, that means that we're at a point on a vertex of at least for SUN, on the vertex of the product of the 3 simplices. And of course, if such a point lies on P, it must also be a vertex of P. One polyhedron is contained in another. As I said, these things have a lot of symmetry. There's an obvious action of the central elements. I could just multiply by, flat connections with values in the central elements. So this group is isomorphic to 2 copies of the center. And this preserves P, and the vertices that I just discussed here are just the orbit of the trivial vertex. So let's call those the central. There's also an action of the symmetric group on 3 letters, right? That just permuting A, B, and C. And that's okay, because if I exchange A and B, I got some other C which is conjugate to the one I stole. So what are the vertices? At first you can crank them out by hand, then you can use a computer, you could ask, Belkale's recursion and polymake to tell you. For SU2, we have the tetrahedron, and the only vertices are those central vertices, right? Every vertex of the polyhedron was also a vertex of the cube. For SU3, this again turns out to be true. There are exactly 9 vertices, and they're just all in this one orbit. For SU4, we have the first example, and it's extremely simple, where there's a vertex of this polyhedron that does not come from the center. Here are these 3 matrices, right? Their product is evidently 1, they're in SU4, but I can find that their common centralizer is, of course, the maximal torus that they lie in, the diagonal matrices. I can find elements of those things that act non-trivially on the eigenspaces of the first one, but trivially on the eigenspaces of the latter 2, and so on, right? Namely, this torus. So that's what makes it a fixed point. And if you think about the case of SU4, you see that this is the only other orbit of the vertices. Once you understand the central vertices and you understand these vertices, then you have them all. For SU5, you have a similar situation. Here are the matrices in question, and you see all I've done is added a column of 1s to the beginning. And of course I can keep doing this ad nauseum, right? I can keep doing that. I will get fixed points. It's not totally clear that it's still a vertex, which is an extremal fixed point, right? But it's some fixed point of the torus action on this master space. So I refer to that as dilation. When you simply enlarge the size of the simultaneous eigenspaces, you can keep doing that with any of the simultaneous eigenspaces. But we're still in a relatively felicitous situation where all of the fixed points in the master space are extremal fixed points. They map to vertices and not to interior points of the polytope. And they all come from commuting triples. I mean, these are diagonal matrices, so they're all commuting. And there are only 2 orbits of this symplectic. For SU6, there are 4 orbits, even when we take into account the further action of the symmetric group. There's the central orbits that I mentioned before. There are the ones that you get by dilating the previous example, and you can dilate in 2 different ways. You can enlarge the first eigenspace so it has dimension 3, or you can enlarge 2 eigenspaces so that they both have dimension 2. But even after you do that, there's still one completely new one. And here it is. It involves 6 roots of unity. And, you know, you can, as an exercise, you can work out that there are diagonal matrices acting non-trivially on the eigenspaces of any one of these, but trivially on the eigenspaces of the other. So, I mean, this point of view just makes us think generally about what you might call abelian vertices, the vertices of this polytope corresponding to commuting matrices. And once again, the geometric interpretation is that it splits into sum of flat line bundles, at least for this unit. Now, as I mentioned, it's not necessarily the case that every fixed point in the master space maps to a vertex. But if it is a vertex, we'll call it an abelian vertex, and all the vertices we've seen so far are abelian. The space of flat T bundles, let's think about flat T bundles instead of flat K bundles. I mean, it's the same as before, right? Only there's no issue with conjugacy. It's really just a product of 2 tori. And that is mapping to P in a natural way by taking the conjugacy classes of A, B, and C. And I can lift it up to the universal cover, to the algebra. It's clear that this is going to be a piecewise linear map from this vector space to the polyhedron P. What is it? Well, you keep asking about SU2. In the case of SU2, the image of this map, you know, T is 1-dimensional, T times T is 2-dimensional. It's mapping to this 3-dimensional space. It can't map onto the whole tetrahedron, but it maps exactly onto the boundary of the tetrahedron. And it's kind of an interesting thing to think about. You can think about this in any dimension. I have T times T, mapping into delta times delta times delta. It maps, you know, locally to a linear subspace, but every time it hits the wall, it reflects off it using this usual rule in physics that the angle of incidence equals the angle of reflection. Because what's really happening is it goes through the wall, but then you bring it back with an element of the affine Boyle group. And it's an interesting question. It's like crumpling up a piece of paper and throwing it in there, right? It's piecewise linear. Well, each time it hits the wall, it reflects off the wall. You know, what is the convex hull of such a thing going to look like? There's going to be some polyhedron, you know? Is there a chance that it could be our polyhedron? Well, for SU3, that works beautifully again. It does not stay on the boundary, it goes into the interior, but it does hit all of the vertices. For any K whatsoever, the abelian vertices are just the images of the points, you know, which are the vertices of the regions of linearity of this map, right? I mean, that's again just a triviality. That's how you're going to get vertices from commuting matrices. So it's completely clear, since the map only changes direction when it hits the boundary of the of delta Q, that these vertices all lie not only on the boundary but actually on the R skeleton. To get a vertex here, I really have to hit several facets of the boundary. So these vertices all lie on the R skeleton of this product of symbols. And there's a more, you know, slightly more broader way to think about it. Let me define a periodic chamber decomposition of a finite dimensional vector space to be just a locally finite collection of hyperplanes, which is periodic, like a wallpaper pattern when you translate it by some lattice of full rank. And then a vertex of such a thing, I'll define to be just a vertex of one of the polyhedra that appears as a chamber. And of course, if I mod out by the lattice, then there will be finitely many vertices. I can think of it as like a chamber decomposition of the torus. Now, a union of finitely many such things is again one of these such things. And if I have a linear surjection of vector spaces, I take the inverse image of such a thing, I get such a thing. And the key example that you're supposed to keep in mind is of the maximal torus of a compact Lie group, together with the hyperplanes, which are fixed by one of their reflections in the affine Weil group delta. So call this C. We saw it once before for SU3. There it is, right? That's the chamber decomposition of the Lie algebra T that I have. So now, the question I want to raise is, on the direct sum of two copies of the Cartman algebra, consider the union of these three periodic chamber decompositions, the one coming from the first factor, the first sum n, the one coming from the second sum n, and then the inverse image under the sum map. And I put them all together. What are the vertices of that? How do I classify those vertices up to translation? I don't know. And, when I start thinking about the cases of SU5, SU6, I see the things that appear as vertices. Is this an easy question? I hope it's an easy question, but it's something where I don't know, and, the lead theorists that I've asked don't know. So if you know, tell me on the train. So really, all I'm going to do for the remaining time is just make various, random disconnected observations about how to find vertices. Vertices of the polyhedron. I don't have any grand unified theory. I don't have, as I say, any theorem. I observe, for instance, that there are two infinite families that I can write down, which generalize the ones that I already saw for SU4, SU5, SU6. And SUn squared, here's one of them. You take all of the n roots of unity, and you cycle through them. And then you also cycle through them in a different way. You repeat the first one n times, you repeat the second one n times, and so on. And then let's see, of course, C cycles through them, but in a more complicated way that I was too lazy to write. But you can check it. This has the desired property that there exists torus elements acting, in any desired way on the eigenspaces of one, while acting trivially on the eigenspaces of the other two. Here's the other one, in SU2n. Well, this is the direct generalization of the one we saw in SU6, right? Where you have A just alternating between psi and psi inverse, where I is a 2nth root of unity. And so here there are two eigenspaces, here there are n eigenspaces, here there are n eigenspaces. But cleverly put together in such a way that the desired property is set. So we've already seen them. However, they're not always vertices. You can check, and I did check, that if you go up to higher values of n, sometimes these do lie in the interior of the polytope. So that's, that's bad news. Can anyone think of any more infinite families like this that are of fixed points of the torus action? It's again just an elementary question in linear. Another elementary thing that I observed. This is going faster. Oh, it's good news for us. This is going faster than I thought. It's because Dan isn't interrupting me often enough. Maybe he wants to catch the train too. Another elementary observation is that if you think only about conjugacy classes of order 2, that is, unitary matrices whose square is the identity, well, that means that they are conjugate to diagonal matrices that only have 1s and -1s on the diagonal, right? Then, there's this very simple argument that says that such, if this is true for AB and A times B, then AB equals BA. For this, extremely simple reason. So they may be simultaneously diagonalized. And that means that, in the moduli space of such triples in this conjugacy class, there's only one element, because anything is conjugate to these. And so that means that the moduli space is a point. And those of us who have been, playing this game for long enough know that when this moduli space is a point, that means that you must be on the boundary of the polyhedron where the moduli space is not empty. If the moduli space is a point, then it means it's about to disappear. Alright, so let me not elaborate on that. But these points are all on the boundary of my Norman polytope. But then, they all have diagonal entries which are all +1 or -1. How can I assemble +1s and -1s on the diagonal so that I have, I-1s in A, J-1s in B, K-1s in C? They have to satisfy the Clebsch-Gordon rules which describe the representation theory of SU2, right? If I have too many, if I and J are too big, they have to overlap. If they're too small, they can't overlap enough. So here somehow something related to the representation theory of SU2 is appearing in the study of, conjugacy classes of matrices in SUN. So, it makes me scratch my head. I see no, systematic explanation for this. Is there any generalization of this, say, if I study classes of order 3, or is there anything to do with representation theory of SU3 appearing in this problem? Again, if you know, tell me, but I don't know. Alright, but then once the computer grinds into the mud thinking about SU7, there's some hope on my part. Can I actually beat the computer with pure thought? Can I work faster than the computer, and can I figure out what all the vertices of this polytope have to be for SU7? At least in the, if I'm looking for these abelian vertices. And the answer is yes, there are quite a few constraints on what possibilities are allowed. Enough that I can sort of, just by performing a exhaustive search, I can find them. So recall, first of all, that I have to find a torus inside my group that surjects onto these 3 tori, which are the centers of the centralizers of the 3 elements, right? And a matrix A, which has, if A has n1 different eigenspaces, that means that the center of its centralizer will have dimension n1 minus 1, right? So if A, B, and C have n1, n2, and n3 eigenspaces respectively, then, the dimension of T is, well, for SUN, it's n minus 1, the rank of SUN. The dimension of this is the thing on the right, so I can't have too many eigenspaces in my 3 matrices. They can't, there's this, sums of the number of eigenspaces cannot exceed the whole dimension with, with these, well, in this sense. On the other hand, there are constraints going in the other direction. What if n1 equals 1? That's, to say that the center of, to say that a matrix has only one eigenspace, that means that it's a central element of UN or SUN. And then we saw that for central elements, I guess it's just clear, really, that if one of these elements is central, then the other 2 have to be central. If n1 equals 2, then, with a little bit more effort, you can see that you have to have, the only vertex you can have is that infinite family that I wrote down before in SU2n, or one of its dilations. More generally, if you see a dilation, you can take it away and you go back down to a group of lower rank. And if a vertex is not a dilation, then n is exactly the number of simultaneous eigenspaces of A, B, and C, right? That means that every simultaneous eigenspace is one-dimensional. And so then I have that. But then, how many these are 3 elements that multiply to 1. How many simultaneous eigenspaces can there be? Well, it's at most the number of eigenspaces of A times the number of eigenspaces of B, right? Same with B and C, same with A and C. So I also cannot have too few eigenspaces. You see, this inequality goes in the opposite direction. I'm sorry?
Your n is 7.
My n is, for this argument, my n is anything.
No,
right?
but you said that you are trying to do that.
For n equals 7, yes. If I can beat it for n equals 7, then I can surely beat it for n equals 8, right? But it's going to take me even more time as well. Well then, right. Once I understand this, then the sort of strategy for finding at least these abelian vertices is to first try and find the sort of configuration of possible eigenspaces, and then try and fill in those eigenspaces with eigenvalues, and say, are there eigenvalues that satisfy the criteria that I wanted? So if I first think about the eigenspaces, the eigenspaces, I'm assuming that my matrix, I'm really talking about products of diagonal matrices now, which is an extremely simple topic, right? The eigenspaces of diagonal matrices are coordinate subspaces. And what I'm looking for is triples of coordinate subspaces satisfying certain criteria. So I really have three partitions of the set of natural numbers between 1 and n. But here I mean partitions in the sense of subsets. So it's not really the same as the thing that there's, you study with McMahon functions and so on. It's a different partition in a more naive sense. And this triple of partitions would satisfy, the condition that I was discussing before, oh no, I didn't discuss it before, but what is it? If I have a simultaneous eigenspace of, of A and B, well, that's also a simultaneous eigenspace of A and C, right? If the eigenvalues of A and B in that eigenspace determine the eigenvalue of C, and conversely, those of A and C determine the eigenvalues of B, and so on. So I need something like this. But also, there's another phenomenon like dilation, but a different phenomenon. If one of the eigenspaces, say of A, is contained in the eigenspace of B, then I can divide out by it, and I get a similar example in lower dimension of something satisfying these criteria as well. So to look for the sort of irreducible one, it's not dedilation, what should I call it? Shrinking or something. Without loss of generality, I can assume that no one of these spaces is contained in another one. And this leads to some kind of graphical calculus. That's why I have this piece of chalk in my hand. You see, so for SU7, I need to, using those inequalities in both directions that I had last time, and ruling out the cases that I understood, the only remaining case is that A, B, and C all have three eigenspaces. So the way the graphical calculus works is this. A, B, and C have three eigenspaces each, so I draw a 3x3 grid. I think of these as the eigenspaces of A, those are the eigenspaces of C. But I want a space of dimension 7, so I want to black in 7 of these boxes, which are going to be the actual simultaneous eigenspaces. And now I'm going to ask, well, what eigenspaces can I have for C? Well, because of this exclusion principle, I'm only allowed to connect them up by diagonal lines. And if I partition 7 into 3 parts, none of which has size 1, then one of them must have size, but 1 is ruled out by that. So then one of them must have size 3. Now without loss of generality, I can act by the permutation group Sim3 acts in 3 different ways here. So I can assume that one of them is on the diagonal, right? Now I just have to fill in, 4 more boxes in such a way that this exclusion principle is not violated. So there is no column and no row that contains only a single box. Well, that means that some row has to contain 2 boxes, and with the, using the action of the symmetric group, I can assume without loss of generality, it's the middle row. And then this question is just where do I put the last 2 boxes? So as not to violate the exclusion principle, I have to put one of them either here or here. And again, without loss of generality, it might as well be here. So then the only question is where does the last box go? If it goes here, then the only way to connect them up, again, modulo some symmetry, is this. And so there's really only 2 possibilities of type 333, and they're this, and, sorry, what's the other one? This, right? And again, to avoid violating the exclusion principle, I have to connect them up like that. So then I know that that describes my eigenspaces. Now can I fill in eigenvalues in such a way that I have the desired property? That I liken to a Sudoku, or it's really more like a magic square. I have 3 elements in SU7, so I take a 3x7 box, and I have to fill it in with unit complex numbers in such a way that all the rows multiply to 1, so I get matrices in SU7. All the columns multiply to 1, so I have A times B times C is the identity. But also, because of these rules, some of the boxes have to be filled in with the same number. So it's a kind of a fun game when you play it. But I have no systematic understanding of, where it leads. You can find, well, I can find what I think is a complete set of all the vertices for SU7. As I say, I've beaten the computer. However, I thought this was the case, and I got a little bit shocked that, for a long time I thought I had an argument to show that, I thought that all vertices were abelian, that they all, for SU2, SU3, SU4, SU5, and SU6, this is true in the computer tells me so, right? So, experimentally it's true. I thought there was even some argument to prove it, but it's not true. Here are the examples. Well, these are the Pauli spin matrices, we know them. And sigma 1, sigma 2 equals sigma 3, but they don't commute. They almost commute, right? Their commutator is in the center. But for SU8, I take these matrices, which are not diagonal, they're block diagonal, but they have these non-commuting things on the diagonal, okay? And you can check that this satisfies this property, and then you can check against Belkale's inequalities that they lie in P and they are in fact a vertex, they lie on the diagonal in fact. And so they're all three, A, B, and C are all conjugate to each other. And this also lies on the skeleton. One question you might ask is it true that all vertices of P actually lie on the R skeleton of delta Q? Again, I know of no counterexamples. This, all the abelian vertices must by the argument that I gave, but then so does this one. Now, I've talked to you for a long time. All I've talked about really is about arguments involving completely elementary Lie theory and, linear algebra, and combinatorics. The truth is there are a lot of deep ideas that are, potentially related to these ideas. And if I was careful, I would touch on two of those things. Okay. Now is the time, if you want to catch the train, right? You have actually, a little less than 7 minutes. So, take a 15-second break to let those people go. Yeah, but I'm coming to my grand peroration anyway, right? There are two much more sophisticated, subjects in mathematics that these are related to, and one should, in principle, discuss these, but I won't. One is that, in the symplectic theory, you're not just interested in the image of the moment map. You're interested in a piecewise polynomial function supported on its image, which is the symplectic volume. The Dorsey-Heckman theorem says that inside these polyhedral regions where there's no topology change in the symplectic quotient, then the symplectic form varies in a linear fashion. And so if you take its top power and integrate it, that's the symplectic volume. That varies in a piecewise polynomial fashion. Where there are jumps not only on the boundary, but also on some internal hyperplanes. And really, one should try and determine what is this piecewise polynomial function supported on P. One should not just ask about P. And there is some work in this direction by Eckhard Meimek, and I actually don't know so much about it. In a way, this is, when you have a piecewise polynomial function, you try and write down an implicit formula for it, you're more likely to end up writing down a formula for its Fourier transform. And that's going to involve enumeration of the facets, not the vertices. So maybe it doesn't have so much to do with what I talked about. The other thing that should have a lot to do with it is algebraic geometry, right? This is a meeting on algebraic geometry. The first thing you learn in most lectures about flat connections on surfaces is that there is some correspondence theorem relating a flat bundle on a trinion or indeed any Riemann surface with boundary to an algebraic vector bundle on a punctured curve, in this case a thrice punctured P1, carrying something called a parabolic structure and semi-stable with respect to that parabolic structure. I completely suppressed that, right? I didn't tell you what parabolic structure is, but that means that the whole question somehow turns into questions about algebraic geometry, about the existence of semi-stable bundles with given weights. And the vertices should correspond to parabolic bundles with some kind of rigidity property, but it's a little hard to put your finger on what that rigidity is. It's not saying that they have no infinitesimal deformations, because, you know, they're strictly semi-stable. You can deform them to extensions and so on. But worse than that, I mean, all the interesting vertices that we want to get our hands on turn out to lie on, you know, in this vile alcove. There is one wall that does not pass through the origin, and that's the wall that really, you know, complicates the picture and makes things much more subtle. It turns out this correspondence theorem for you know, flat connections where one or more of the holonomies lies on that wall, the correspondence theorem is much more subtle. You don't have a vector bundle or a principal bundle anymore. You have what's called a parahoric bundle, which is a torsor over some sheaf of groups, which is locally modeled on parabolic subgroups of the loop group. But those parabolic subgroups, you know, do not have to be the familiar ones that that are subgroups of the standard parabolic subgroup of the loop group. They could be more exotic. And so then even formulating, you know, the category of parahoric bundles, for instance, I think is not an abelian category. Oh, thanks. But anyway, and certainly formulating what you mean by the rigidity is, you know, is not going to be easy. So I tried to pursue this to some degree, but without success. Yeah. Oh, well, that's it. Since I have now missed my train, there really is only one thing that remains to be said, which is, can anyone give me a ride to Unconquer? And actually, I do mean that seriously, but there's another much more important thing to say, which is that the organizers have done a wonderful job organizing this delightful event, so thank you very much to them. Thank you.
For some questions from the speakers to use this train anyway.
Yeah.
How many vertices do you have in total? Like for n equal to 6, 5, 4?
I don't have those numbers at my fingertips, but it's large, in the thousands, right?
But is there any combinatorial mean just to the sequence of numbers that you get?
Should I look at? I looked it up on Sloan's index of integer sequences, for example. I mean, no. You know, yeah, I don't know. I mean, the first few, you know, you have this very high degree of symmetry, so you somehow have to take account of that. For example, you always have these central vertices, and those central vertices are n squared in number. So, you know, if the tetrahedron has 4 vertices, the polytope for SU3 has 9 vertices, then the one for SU4 is going to have 16 of those vertices, but it's then there's that other orbit that I mentioned, and, you know, what's the stabilizer of that orbit under this group? I have to think about it. But it might be 32. The stabilizer, you know, it might have freely on that one as well. Yeah, but it's, I mean, no, I'm completely unaware. Again, I would be, you know, all ears if you have any ideas about what a combinatorial interpretation is.
But the complexity here is so you don't have bases and vertices, I think it's the same type of complexity.
Yeah, that's right. There's not that much data, right? Because already in the case of n equals 7, it's already intractable. Also, right, yeah, the number, as I said, even should ask Belkale this question. I don't know if Belkale had the formula for the number of facets. He might. But he has these two things, right? He says that the facets are in one-to-one correspondence with these Gromov-Witten numbers that equal 1. And then he has some completely explicit recursion that gives you a finite list, including the facets, but including something else as well. So, yeah, I'm not sure. Yes?
Is the vertex problem solved for positive column problem?
For positive?
Yeah. You have this column problem for the classical column, and the number of vertices in the corresponding polytope known.
You mean the additive?
The additive problem.
Yes. Not to my knowledge. I mean, so, I did not mention the additive form of the problem at all, but of course the additive form of the problem is the one that was actually stated and discussed by Horn. It was the classical form of the problem. And that's, you know, corresponds to taking snipping off this polytope very near the origin, right? Taking a cross-section of this polytope very near the origin. So you have, you know, it looks like a cone, and you take the cross-section of the polytope. In other words, you're asking how many rays emanate from this polytope at the origin. Again, I do not know the answer to that. I know, well, I'm fairly sure that the answer is not no.
If there are no further questions, there are two things I want to say. First, I would like to thank all of you for remaining for the last lecture. And second, I'm told by the nebulous ephemeral notion of organizers that there's in fact one person who carried everything on his shoulders, and that's Jason. And I'd like to thank the speaker. So let's thank all.